Hey guys, welcome back. We're talking triple integrals and we're talking about them using cylindrical coordinates. And so this next example is a pretty short one. It says let's use cylindrical coordinates to set up the triple integral of e of y dv, where e is the solid that lies between the two cylinders of x squared plus y squared equals 1, x squared plus y squared equals 4. We're above the xy plane and we're below the plane of z equals x plus 2. So the first thing I want to say is that since we're above the xy plane, so right now the xy plane lies right here. And so since we're above the xy plane, we know that this means the lower bound of z is actually going to be 0, right? Because it's in the xy plane, so z is actually 0 here. And then we're actually above our volume, right, by the plane of z equals x plus 2. So that's really saying that we have a plane that's going to come out like this. And this is be our top region right here. So x plus 2. So we can also say that the top of our surface is going to be z equals x plus 2. So we can already see that based on those two equations that our z is going to be bounded by 0, which again is the xy plane, and then the other plane of x plus 2. Since we're looking at cylindrical coordinates, we're going to modify this very so slightly, and we're not going to use x. We're going to use that x is equal to r cosine of theta, and that's what we're going to use for our upper and lower bounds for z. Then we're going to look at our cylinders for x squared plus y squared equals 1 and x squared plus y squared equals 4. So the cylinders are going to be in between these two planes, and I don't need, you guys know I don't draw well at all. So it's going to look something like this. So our two cylinders are inside of that, right? It's between the two planes. But what we really just need to visualize here is that x squared plus y squared equals 1. Well, that's the same thing as r squared is equal to 1. And so that means that r is going to be 1 in this first part. And we're actually just looking at, the region in between the two cylinders. So this little guy right here, if I want to highlight that a little bit better. And so then we also can say that the radius squared is equal to 4. So the radius will be 2 here, right? So the radius in the region we have is going to be in between 1, which is this inner circle, and then the outer circle radius equals 2. So now we can say that the radius is going to be in between 1 and 2. And then our last thing that we need to put together here in this problem is what's going on with theta, right? Well, it's the entire cylinder, right? It's going around the entire region. It's going around the entire xy plane. So therefore, in this case, our theta is going to be between 0 and 2 pi. So then when we tie everything together here, we're going to just go ahead and set up, because it's just asking us to set up the integral. So we're going to go ahead and do the integral, and we're going to start here with our theta, which is going to be 0 to 2 pi. Then we're going to write an integral for our radius, and that's going to be 1 to 2. And then we're going to go ahead and write our functions for z in polar coordinates. So remember, make sure it's in polar coordinates, or sorry, cylindrical coordinates, using polars. So we're going to do that. This is r cosine of theta plus 2. So since we're saying that, we also need to remember that y is going to be our sine of theta. And then we're going to add our r, and then dz. Sorry, let me erase that. dz, dr, and then d theta. And so this is the setup for this problem. So we're going to leave it right there for that one. I hope you guys enjoyed that, and we'll see you in the next video where we do a little bit more complicated problem. So have a good one. Take care.